All right, hey guys. Hope everybody's doing really well today and excited to do some optimization day two. I'm gonna try to talk like the Khan Academy guy, but I don't know. We'll see how it goes. Maybe I'll put my little spin on it. I'm not good at this because it's really awkward teaching in front of like nobody. So you just be patient with me. We got this. Okay. I'm gonna start off today. I'm gonna try to do the videos like I guess as short as I possibly can. I don't really want to overdo you too much, so I should probably get into it here soon. But again, I'm just gonna try to explain everything. If it's too fast, pause the video, and we can go from there. I plan on answering any questions tomorrow, so let's just see how we can do. All right. Okay. This is actually so the last example from Monday. I wanted to do this one real quick, make sure we're good on this, and then I got four more examples um, for today. Okay. So it says find the point of the line 6x plus y equals 9 that is closest to the point negative 3 comma 1. Very common question I'd like to ask in terms of like an equation or something like that. So it's pretty cool. I kind of want to draw out first of all what's going on here so we can kind of visualize it. Okay, so we're looking at the function y equals. I'm just gonna get this in a graphable form. That's just negative 6x plus 9. Okay, and we're looking at that in relation to the point negative 3, 1. So if I were to draw that graph out a little bit here, okay, negative 3, 1 is right here, and my function negative 6x plus 9. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's slope of negative 6. So 1, 2, 3, 4, 5, 6 over 1 looks something like this. Okay. All right, so what this question's asking me is like, okay, if I got this function here, y equals, and I got this dot right here on the left, what is um, what is the point on this curve? So this y equals curve, somewhere on here, where is that point that is closest to my point, negative 3, 1? Where is that point at? So I guess what we're trying to do here is we're trying to minimize, okay, we're trying to minimize distance, right? We're trying to minimize the distance between that point to a point on my curve, okay? It's not going to be up here. It's going to be somewhere down right here, right? That's kind of the shortest line drawn there. Well, how do I minimize distance? So this is what I'm trying to figure out. That's going to be my Q equation. So once you draw your picture, once you figure out what you're trying to do, the question is what is Q going to be? Okay. Um, well, in this case, Q is what I'm minimizing is distance, right? Do I have a formula for distance? Absolutely. We have the distance formula. Distance equals the square root of um, x1, oops, x1, got to get my red, x1 minus x2 squared plus y1 minus y2 squared, right? So that right there is going to be my Q equation, all right? Now, the thing about this equation is remember that for Q, okay, Q's got to be two things. It's got to be one variable, and it's going to have to be simplified. So right now, it is not one variable. We have both x and y in it, and it's not simplified, obviously. Okay, so we're going to have to get this all in terms of, I usually prefer to get it in terms of x. Now, one thing I'm going to say that's going to help this problem out just a little bit, okay? Our variables here are x and y, x2, y2. Those are our variables, okay? And d is just going to be some quantity. It's just going to be some distance that we're going to find, right? Here's the thing that's going to help simplify this down a lot here at the end is you can go through and take the derivative of this equation, this square root equation. It's going to work out and give you the right answer. But it actually turns out that because d is just some constant, and the variables that I'm relating together are just these, x and y's, I can go ahead and write this as d squared equals, and then square both sides to make it just this. And that's going to be my Q equation. And the reason that I can do that is because when I take the derivative, I take the derivative of d just like I would with y, it's just going to go to 0 anyway. So squaring it is not that big a deal. It's not going to change the value or the relationship of the problem. It's not going to change the answer that you're going to get. All right, and that makes our derivative, finding our derivative, that much easier. Okay, so really our Q equation that we can solve is just this one right here. If you don't like that and you want to do the square root one, you're more than welcome to. Okay, all right, but our next question is like, all right, how do I get this to one variable? Okay, so well, first of all, if I'm talking about finding the distance, it's the distance between 2 points. Well, 1 point is given, right? We got 1 point, we got 1 x, and we got 1 y, right? So go ahead and substitute that point in, and you can substitute it as x2, y2, or x1, y1. Just how I did it was x2, y2. So I'm going to say that q equals um, x minus, and then the x value was, what was the x value? The x value was 3, so that'd be x plus 3 squared, and then plus y minus 1 squared. So that was just plugging in our points, right? Now the other issue that we have here is though that we still have x and y. It's not one variable yet. So how can I substitute something in for that y? Well, how about y equals negative 6x plus 9? That was given at the very beginning of the problem, right? There's my y that I can plug in. So now if I were to plug that in, I got q equals, that's x plus 3 squared plus, and now y is actually negative 6x plus 9 minus 1 squared. And there's my q equation. There it is. That's all it is, right? Well, we can check off the whole one variable thing. Now it's just got to be simplified, and then we can do it. Well, simplifying is not too bad in this case. Q equals x plus 3 squared plus, and only the simplification I really need to do is inside this fraction, right, or inside this parenthesis. So there we go. Okay. So now I got a one variable, I got it simplified, and it's not too bad. I can just take the derivative, and we're trying to minimize it here, so we're trying to find a minimum value. Okay. So in this case, I'm going to have q prime equals, and it's two chain rules, right? So we got 2x plus 3 to the first, and then times the derivative inside, that's just 1. And then plus 2 negative 6x plus 8 to the first, and then times the derivative inside is negative 6. Okay. So you can pause the video and take a second and simplify this out, FOIL this out, do whatever you need to. But it actually gets down to, oh, and this is equal to 0. It actually gets down to, from what I see, I get down to, what do I get down to? I'm looking on my notes. I get down to x plus 3 plus 36x minus 48 equals 0. So I get down to that, which reduces down further to 37x minus 45 equals 0. So then x equals 45 over 37. So that's the x value on my curve, all right, that's closest to that point, negative 3, 1. If I want to figure out the y value, I can just simply plug it back in and figure it out. But before we do that, I think it's important that we test, and we test to see if that point is indeed a minimum. So I'm going to consider q prime, and I'm going to consider this point 45 over 37 on this number line. And remember, if I'm trying to test it out, I'm just going to plug it back into my derivative function. Like if I were to plug in 0 into that, I'd have a negative number. If I plugged in a big old positive number, 100 or 200 or something like that, it's going to be positive. So by the first derivative test, okay, we know that it is a relative minimum. And an absolute minimum because it only sign changes once and we're on an open interval, right? So we got the x value. If I want the y value, just simply plug it into your equation from the beginning. Remember the equation was negative 6x plus 9. If I plug my x value into that, it's y equals negative 6 times 45 over 37 plus 9. And I end up getting the point, I got 63 over 37. Okay. So what we just found was the y value. So our coordinate point is 45 over 37, comma, 63 over 37. It's at this point right here that we are closest to the point negative 3, 1. All right, so this point right here that we just found, again, was 45 over 37, comma, 63 over 37. Okay? And we did that by minimizing the distance formula. That makes sense. Any questions? Well, I don't know if you have a question. Okay. Yeah, so again, the step was finding our Q equation, getting it one variable, taking the derivative, and finding that critical point, and just testing to make sure it is indeed a minimum. Okay, let's keep going. All right, I'm trying really hard here to decrease this video. So let's go through this next example. Again, another common example that we kind of run into, and see how it goes. So it says a farmer has 800 feet of fencing and wants to enclose a rectangular area for a pen. He is going to divide the area into 4 pens using the fencing with each side parallel to the same side of the rectangle. Find the maximum area he can enclose. That's a very wordy problem. Let's start by drawing the picture out. So we have 800 feet here. It says we got a rectangular area for a pen. So let's draw that out first. Here is my rectangular area for this pen. I'm going to call this X. I'm going to call this Y. And it says he's going to divide the area into 4 pens using the fencing with each side parallel to the same side of the rectangle. Okay, so if I'm dividing it into 4 pens parallel, that's 1 pen, 2 pens, 3 pens, and 4 pens. So those are all parallel to one side. And honestly, you could have done it the other way. It would have worked out just fine. But I made it parallel to this side, and there's 4 pens, right? So each of these 4 pens have length X, right? And we have a width there of length Y. Okay, so there's my dimensions of this rectangular pen. Now, once you draw your diagram, you got to think about, what are we trying to optimize here? What are we trying to maximize in this case? We're maximizing area. So once you draw your diagram, the first thing you want to do is just give an equation of the generic thing you're trying to maximize. I'm trying to maximize the area of this rectangular pen. Area is just equal to length times width. That's it in its most basic form. Okay, this is going to end up being our Q equation. Okay, so the first thing we're going to have to do, so we determined that Q equals length times W. The first thing we have to do is, well, go through our steps and figure out what makes it one variable and how we can get it simplified. Okay. Well, if I'm trying to get it one variable, a good place to start is the fact that length and W, length and width, is just Y and X. That's all that is. So Q equals X times Y. Okay. All right, so we got that it's in terms of X and Y. Now we're going to have to really isolate it. We're going to have to get it in terms of one variable. Well, how the heck can I do that? Okay, how can I get something substituted in for Y or for X to where it's just all X's or all Y's? Well, we're going to have to use extra information given to me. Okay, I'm worried about, I got the area here, but look at all these X's and Y's in my diagram. How can I combine that together to figure out how to substitute X and Y together? Well, it's all going to come into fact with this 800 feet. Okay, all the material that I've used here, all 1, 2, 3, 4, 5 X's and 2 Y's, all those materials are going to add up to my 800 feet of fencing. Well, there's my equations where I can isolate it. I know that all 2 Y's and 5 X's is going to give me my perimeter of 800 feet. Okay, and I usually like to get it in terms of X, so I'm going to get Y by itself here. So 2Y equals 800 minus 5X, or Y equals 400 minus 5 halves X. Okay? And it's this equation here that I can substitute in for Y. So now Q equals X times 400 minus 5 halves X. All right, great. So we got it one variable, and now I want to simplify it so I can take the derivative. So q equals, and to simplify it, just simply distribute the x, right? It's going to be 400x minus 5/2 x squared, okay? So we got it simplified and we got it one variable, and I'm trying to minimize the area. So this is my area formula in terms of x, and I'm trying to minimize it, which means I'm trying to find a minimum value. And we know how to find a minimum value. It's just the derivative. So x prime equals, and that's just 400x, and then minus 2 times 5/2, wouldn't that just be 5x? Okay, oops, and I'm sorry, that should be just 400. Derivative of 400x is 400. So my derivative overall is 400 minus 5x. And solving for x is no problem there, right? 400 equals 5x, or x equals 80. So I got my dimensions, I got my length, okay? Now, I got to make sure that's a minimum, so we always got to make sure to test it. So I'm going to test 80, okay, on my number line here, and I'm going to test it in my derivative function, just like I would anytime I'm finding a minimum. If I plug in 40, that's going to be, oh, and actually I'm trying to maximize this. I apologize. That should be a maximum value. So if I plug in, say, like 40, that's going to be a positive number. If I plug in like any number greater than 80, like 100 or something, it's going to be negative. So this is indeed a relative max. Okay, we've just shown that. Okay, so we got a relative max, and now if I want to find the other dimensions, if I wanted to find the y dimension, then I could just simply plug it back into my y equation over here, right? I can say that y equals 400 minus 5/2 times 80, my x value. And plugging that into our little my little calculator thingy here, I get y equals 200. So that means that, like, if I had this pin here, the dimensions that maximize the area is, we found x to be 80 and this to be 200. 80, 80, 80, and yes. Okay. So the question, though, specifically asks for find the maximum area. So if I want the maximum area, well, we got the formula length times width. So my max area equals 80 times 200, which is 16,000 feet squared, I believe. Okay. So there's my resulting max area with the given dimensions, 80 by 20 feet. That wasn't too bad, right? It was just length times width again. That was our maximum area. We got it in terms of x only. We took the derivative, set it equal to 0, and solved. All right, this next problem is, again, not too bad at all. Okay, so it says find a positive number. Find a positive number. So that means I need to have a number greater than 0 such that the sum of the number, okay, so the sum of the number and twice its reciprocal is as small as possible. I'm trying to find some number that if I were to take it and add it to twice its reciprocal, it's going to be as small as possible. So I'm trying to minimize something. I'm trying to minimize something. So the good thing about this is it gives us what we're trying to minimize. It gives us the equation. All right, it's trying to minimize the sum. So the sum of a number and twice its reciprocal. That's the function I'm trying to minimize. It straight up gave me that. All right, so this right here is my Q equation. All right, so Q equals, so Q equals x plus 2 over x, right? So you got to ask yourself, is that one variable? And is it simplified? Well, yeah, it's one variable. And if I want to take the derivative, I think the best way to view it is x plus 2x to the negative first. And now it's simplified. So I'm trying to minimize that, which means I'm trying to find the smallest x value on that curve. So I'm going to take the derivative. Q prime equals 1 minus 2x to the negative second equals 0. And solving for that is not too bad at all, right? We got 1 equals 2 over x squared equals 2, and x equals plus or minus square root of 2. So we got two values here, but think back to our domain. What is the issue? What do we have to reject? Well, it's only positive numbers, so I have to reject negative square root of 2 because it's not in our domain. Okay? So we only have one value here. X equals the positive square root of 2. And if I want to test to make sure that is indeed a minimum value, I'm going to do, well, not f, but I'm going to test it on my curve, q prime. And just to make sure, so positive numbers, so maybe I'll try like 1 in my derivative. And again, I'm testing it in this function here. Okay. So that's 1 minus 2 over 1 squared, which is going to be a negative. And anything greater than that's going to be 1 minus a small fraction, which is positive. So this is indeed a relative min by our first derivative test. So if that's the case, then we have just found our answer. It was just asking to find a number. We don't have to plug it back into anything. We found the number. The number is square root of 2. Okay? That is the number that if I were to plug it into x plus 2 over 1 divided by x, if I plugged it into that, it's going to be the smallest value. You can test any other point you want, but square root of 2 is going to be the positive number that makes it the smallest value as possible. And that wasn't too bad, right? Dang it. Okay, so we are down to 2 more examples. I'm at 20 minutes, so I'm really going to try to get, I was trying to get this under 30 minutes, and I'm still going to try. Let's go with number 2. Number 2 is a very common problem. It might show up again on like a test or something. Okay, so make sure you really pay attention to this one. It says find the maximum area. Okay, so area, we know what area is, of a rectangle. Okay, so I'm going to stop right there. I'm going to stop right there because my Q is just going to be the area formula, right? All right, I'm trying to maximize area, which is length times width. If I always start by either writing the generic form of what I'm trying to maximize or draw a diagram. In this case, I just wrote down what I'm trying to maximize. But the area I'm trying to maximize is the rectangle inscribed between the x-axis and the function negative x to the fourth plus 3. So if I were to draw this out, right here, and you can graph negative x to the fourth plus 3, but it's all it is just the negative makes it an upside down parabola at a y-intercept of 3 or a vertex of 3. So it looks something like this. Okay, and you can graph it. That's the generic shape that you get. Okay. And if I'm inscribing a rectangle in that and the x-axis, well, here is the x-axis here, right? It's inscribed by that and a rectangle. So if I were to draw this rectangle, I'm inscribed by this function, so that means I'm not going past the function in any direction. So there's my rectangle. Okay, there's my rectangle. And I don't know what size rectangle is going to give me the biggest area in this function. It could be this rectangle, it could be this rectangle, or it could be the red rectangle I drew. There's some point at which I have a maximum area. All right? And that's what we're going to find. Okay. So let's think about how I can substitute in values in for L and W, right? Because the whole idea, whenever we figure out our Q equation, is to get it one variable and to get it simplified. Okay. Well, all right, so let's think about our length and our width. Well, this right here is my length, and this right here we'll say is my width. Okay. Well, how can I figure out these 2 points? Well, that's not too bad because think about it. If I'm considering this point right here, I'm considering this point as x comma y. Well, at this point, the width is just y, right? So I got the width is y. Well, what is this value then? It's not going to be necessarily just x, because if it was just x, that means we'd be starting from the origin and going over, right? But it's like I have a length of 2 x's. So my length is actually 2x. There's my Q equation. There's my Q equation in terms of x and y. But, again, I needed one variable. How can I figure out what's going to go in for one of my variables? Well, at the very beginning of my problem, I'm given a y equals equation, right? Negative x to the 4th plus 3. I'm going to plug that in, just like I did for my first example. So if you're ever given an equation, that's going to be something you can substitute in. So I got Q equals 2x times negative x to the 4th plus 3. Okay, that's my Q equation. That is my area function that I'm trying to maximize, and it's using the parameters that it's inscribed in between the x-axis and this function. Where the function came into play was substituting it in for y. Okay. All right, so it's one variable check, but it's not simplified, and that's not a bad simplification. Let's just distribute our value. So I got Q equals negative 2x to the 5th plus 6x. Okay, so that's my Q function. That's what I'm trying to maximize. So let's take the derivative, set it equal to 0, and solve. Okay, so that's going to be Q prime equals, what's that, negative 10x to the 4th plus 6 equals 0. And we only got one variable here to solve. That's not bad. That's just negative 10x to the 4th equals negative 6. X to the 4th equals 6 over 10, or 3/5. And finally, I'm going to take the 4th root. So if I take the 4th root, I'm left with the 4th root of 3/5. And that is plus or minus. Okay. Now, remember, the thing is that I'm talking about a distance here. I'm talking about a length. I could do the negative one or the positive one, but in the original graph here, I was looking at this point. So I'm just going to consider x to be the positive 4th root of 3/5. Okay, it's not necessarily that I have to reject the negative one, but when I'm talking about length, I'm talking about the positive one. Okay. All right, so there's my point. That's going to give me a maximum volume. That's pretty much part of the length that's going to give me that x value. Let's just make sure it is indeed a maximum, so I can test this on a number line here, right? The 4th root of 3/5. Okay, and you can test some points of that if you want, but I will say that when I do test points, it's going to be positive and negative. Okay, so it is indeed a relative max. All right, great. So now we got that. We have our dimensions here. Now, if I want the actual maximum area, we can plug it back into our original function, our Q equation, and we'll have the answer. If you want to visualize it a little bit better, you can think of it this way. What we just found was this length right here, right? If I want to know my maximum, I guess if you want to know your maximum volume, all you got to do is just plug it into your Q equation. So like, for instance, Q equals, which is just my maximum area, it's going to be 2 times root 4 of 3/5 times, and then negative root 4 of 3/5 to the 4th plus 3. Okay. And that's just me plugging that x value into my area formula. And if I were to do that, I end up getting approximately 4.225. Didn't give me units, I don't think, so we'll just say units squared. Okay? And that's the max area I can get by inscribing that rectangle. If it asks for the dimensions, well, you can just plug back in and solve for x and solve for y if you want to. but it's not asking for the dimensions. It's just asking for your maximum volume, right? All right, I'm at almost 30 minutes, so I'm trying to get that last example done pretty quick. If you want to find the dimensions of this, just remember the x value would be 2 root 4 of 3/5 by, and if I want to know the y value, you're just going to plug it into your y equation. All right, you're going to plug it into the y equation at the very beginning of the problem, and it ends up being 12/5. But again, it was asking for the maximum volume, and we got that right here. Okay, so let's try that last example. All right, another great example dealing with fencing and dealing with maximum area here. It says, suppose we have a 500 feet of fencing and we want to enclose a field against the wall of a barn. Okay, so here's my barn wall, and I want that to be one of my sides. It says this field is to have 2 parallel lengths of fencing, perpendicular to the wall. So here's one length and one length. So those are 2 lengths of fencing coming out of the barn wall. And then it says it's joined by a convex semicircle opposite of the wall. So these 2 are joined together by a semicircle. So there's your pin, okay? There's your pin that's going to enclose whatever we want, okay? And then it says, how do we maximize the area? How do we maximize the area of this field? That's not too bad at all, right? So we're just trying to maximize area. So if I'm thinking about the area, I need to think about how I find the area of this shape, which is just 2 separate shapes, okay? We have, we'll just call this L for length, okay? And we also have, like, if we have a semicircle, we can think of this as the radius, okay? All right. So then our 2 areas would just be the area of the rectangle plus the area of my semicircle. All right, so if I want to find the area here, the equation that I'm using, area is equal to, well, I got the area of the barn, which is just length times width, okay? And then I got the area of the semicircle, which in its basic form is just 1/2 pi r squared. Okay, so we got the area formula I'm trying to maximize it, but remember the 2 things we have to consider is it one variable and is it simplified? Well, right now it's definitely not, okay? We got 1, 2, 3 variables that we need to get it down to, okay? And so how can I get it down to just 1 variable? It's going to go again based off, just like the other example, this 500 feet of fencing. So I need to come up with an equation that relates L and R together so I can get rid of all these equations. Okay, and so I'm going to use that 500 feet to think about how I can write this perimeter as 500 feet. And we're going to use that equation to substitute something in, and that's not too bad. If I have 500 feet of fencing, that's just equivalent to, well, this L right here and this L right here, so 2L, and this semicircle here, which we know how to find the circumference of a semicircle. That's just going to be 1/2 circumference, which is 1/2 2 pi r. Okay, so let's simplify this down and see what we can substitute in. Okay, if I simplify it down, I got 500 equals 2L plus pi r. And I mean, we can get r by itself, we can get L by itself. I think it'd be easiest to get L by itself and plug it in for r. So maybe I can do like 500 minus pi r equals 2L, or L equals 500, 250 minus 1/2 pi r. Okay, so I'm going to take this function and plug it into L. Okay, so I got that that area equals my length, which is just 250 minus 1/2 pi r times W plus 1/2 pi r squared. Well, the only other issue is that, like, I have r in there, but I still got this W. Okay, I still got this W. Well, how can I substitute something in to where I have all of r's for W? Well, if I'm talking about the width of my rectangle here, the width is just this value right here, okay, which is 1r plus another r. This is just the same thing as 2r. So my area function is area equals 250 minus 1/2 pi r times 2r plus 1/2 pi r squared. So we got it one variable. Now we're just going to simplify it and then take the derivative. So simplifying this down, all right, we just distribute the 2r and we're left with q equals, what's that, 500r minus pi r squared plus 1/2 pi r squared. So now I got it down in terms of one variable and it's simplified. Now I can do the whole process where I take the derivative, set it equal to 0, and solve. So q prime equals 500 minus 2 pi r plus pi r. Okay, and let's keep going from there. All right, so take the derivative. Now we're going to simplify it down a little bit and solve. We can combine like terms as 500. Negative 2 plus 1 is just minus pi r. Okay, and that's set equal to 0. So maybe I can do like 500 equals positive pi r, or r equals 500 over pi. So the radius that's going to maximize that area for me is equivalent to 500 over pi. And you can test that in your first derivative. It's kind of an annoying one to test up here, right about here, okay? And testing it, I'll go ahead and tell you, is going to be positive and negative on the other side, okay? So now if I want, let's see, it's asking for just the maximum area of the field. So if I want the maximum area of the field, we can have the dimensions if you want, or we can just go back and plug it into my Q equation. If I plug it into my Q equation before I take the derivative, I'm going to have my maximum area. So my max area after plugging in 500 pi into that, after plugging in 500 over pi into that, I end up getting approximately 39,788.736 feet squared. Okay, and if you want the dimensions of everything else, you can think about it. It's not asking for the dimensions, but remember our radius was equal to 500 over pi feet. Okay, if I want my width, remember it was just 2 times that. And if I want my length, well, you can go back to the length equation, and you can plug your value in for r, right? It was 500 minus, or I'm sorry, it was 250 minus, it was 250 minus 1/2 pi r, which was 500 over pi. Okay. Which I think if you end up doing that, sorry, it should be a minus. I think if you end up doing that, I think it equals 0. So I think what actually turns out that maximizes this entire thing is if you put one big semicircle. But we can look at that a little bit more later. But the max area would be that right there. Practice some more of this. Stop the video. Try this problem over again. See if you can get what I'm talking about here. And for homework on your worksheet, you're going to do these 5 problems. Okay. You also are going to have access to your review sheet. You can go through and do those, and I'll answer any questions and all questions tomorrow. Smiley face. Hey, I did it under 40 minutes.